Okay, this video is going to go through Avogadro's law and Dalton's law of partial pressures. That's also going to account for looking at vapor pressure of water. So for this lesson, you are going to need your periodic table out. Specifically, you need the back side of that has the vapor pressure of water data table down in the bottom corner. So starting with Avogadro's law, this law states that volume is directly related to the number of moles of gas particles. So when we're writing it in terms of the proportionalities, we could say that the volume is directly proportional to the number of moles. This time we're keeping both the pressure and the temperature constant. So you can fill those out on your big chart there, organizing all of our different laws. So Avogadro's law can be used to determine the molar mass of an unknown gas, and we'll look at an example in a little bit. But first, let's look at Dalton's law of partial pressures. So Dalton showed that the total pressure exerted by a mixture of non-reacting gases, so remember we said that these ideal gases are not reacting in a system. We just have a bunch of different gases, like for example air, that are existing in perfect harmony together in some sort of a container. And the pressure, the total pressure, is the sum of all the individual pressures from each of the individual gases. So therefore we can have this equation P total equals P1 plus P2 plus P3. So P1 might be, for example, the pressure exerted from oxygen, P2 might be pressure from nitrogen, and P3 might be the pressure from, say, water vapor, if we're looking at our air example again. Partial pressure is the pressure caused by the particles of one gas in that mixture. So example number 1 here, 1 liter of oxygen gas at 50 kilopascals and 1 liter of nitrogen gas at 100 kilopascals. What is the total pressure exerted by our gases? So for this case, we can look at the oxygen as our P1 and we can look at the nitrogen as our P2 case. So P total equals P1 plus P2, which is 50 plus 100. Therefore, the total pressure exerted on this system is 150 kilopascals. I can also ask you this question in a slightly modified version. So example 2 here. If 78% of the air molecules are composed of nitrogen gas, what is the partial pressure of nitrogen in the air at STP? So don't let this little STP business throw you off at all. Really what we're just looking at is at standard conditions, what is the pressure from this nitrogen gas? So if I know that 78% of my air is nitrogen gas, then really all that I'm doing is looking at 78% of my total pressure is going to be from that nitrogen. So here we have the 78% converted into a decimal times the pressure at STP. Remember we said that standard pressure is 101.3 kilopascals. Again, you could look at this in terms of torr, millimeters of mercury, atmospheres. Any assessment I will be more specific of what I'm looking at. But let's just go with kilopascals for now. That's usually our standard. So 78% of 101.3 would give me 79 kilopascals, which means that if this is a combination of, it's this one, air here, I also have oxygen and helium and hydrogen and argon and water and a whole bunch of other gases. So that means that 22% of 101.3 gives me the pressure of all of those other gases. So if I was going to look at the pressure of everything else, I could say 101.3 minus 79, which means that 22.3 kilopascals of pressure is being exerted from all of those other gases that are hanging out in my air in combo. Okay, example 3 here. A container holds 35 grams of oxygen gas and 55 grams of carbon dioxide gas with a total pressure of 97 kilopascals. What is the partial pressure exerted by each of the gases? So this one's a little bit trickier because I'm not giving you the molar values. Instead, I'm giving you the different masses. And remember in chemistry, mass doesn't really do a whole lot for us because the mass of each individual atom isn't the same. They're not really comparable. So it's like comparing apples to oranges. So what I'm first going to do here is I'm going to use my molar formula here to convert into the number of moles of oxygen and into the number of moles of carbon dioxide. Once I have both of these in terms of their mole values, then I can actually compare it. So total, I'm looking at 2.34 moles of gas within this container. 1.09 moles is from oxygen, 1.25 moles is from that carbon dioxide. So if we're looking at this mole fraction, really all that I'm looking at, and we've done this before, is I'm looking at percent composition. So if I find the percent composition of oxygen is 47% and the percent composition of the carbon dioxide is 53%, again by dividing the moles of the substance over the total moles times 100%, then I'm basically up to our example 2. So therefore I can just multiply my percent value times the total pressure. So remember, this 97 is my pressure total, which gives me 45.6 kilopascals are being exerted by the oxygen. And then I can do the same thing over here, the mole fraction, or that percent composition of carbon dioxide, times the total pressure to give me the total kilopascals exerted by the carbon dioxide. The other way that I could look at this question, this example here, is just as I did up in example 2. If I know that 45.6 kilopascals is from the oxygen, then I could simply subtract to find the pressure of carbon dioxide would be 97 minus 45.6. And again, that should give me the 51.4 kilopascals as we found up here in this question.